Okay, welcome everyone to this week's OMR Architecture Meeting. This week we have one topic. It's Robert Young will be talking about some of the GC work that is planned for the coming months, if not years. So I'll turn it over to Rob to take us through his presentation.
Okay. Hi everybody. So yeah, let's just get right into it. I'm going to be talking a little bit about the work that's either upcoming or that we have in mind over the year or next few years. So I've kind of broken it into three general categories, which is your future work, which is what we're definitely working on or will be working on soon, and this is more like the concrete activities that are happening in the GC. Then I'm going to start to talk a little bit more abstractly about ways that we could take the garbage collector in the future. And this section is going to be more oriented at pursuing the goal of making OMR generic and usable to more than just Java. And then finally, I'm going to talk a little bit about high-level concepts and the overall architecture of the GC in the future, and one potential way that we might be able to take it. But before I get into that, I guess I should just say a few things about like what our goals are in the garbage collector over the next year. And for the most part, we want to keep doing the same things that we've always been doing. It's the needs of J9 and the improvements that we're making to J9 that are happening in OMR and continue to make the garbage collector better and better. So we're just, in a lot of ways, we're just going to kind of keep doing that. But as well, we want to focus on moving even more technology from J9 to OMR. And that's going to help us, it's going to provide new opportunities for paying down technical debt and finding new ways to sort of clean up our code and sort of heal the gap or fix all the damage that was caused by, splitting the garbage collector in half all those years ago when we started the OMR project. And then, of course, by paying down technical debt and moving more technology into OMR, that should provide new ways to improve our glue APIs, which, I think is going to kind of become this virtuous cycle of continually improving the code because, as things get simpler, then we find new ways to enhance the project, and it just goes on from there. So now I'm just going to talk about the things that we're working on or will be working on in the coming year. So the first thing that I'm going to talk about are the auto-comp builds and how we really just want to get rid of them. Not really just a GC thing, this affects everybody, but in this year, we really need to get rid of those builds and move the remainder of our CI builds to CMake. We need to make sure that DDR support is fully there so that J9 is able to make that transition to CMake. And once we are able to get rid of the auto-comp builds, I think that that's going to enable us to sort of clean up the structure of our libraries and some of our source code. And in particular, I'm thinking about how OMR code, or how the core OMR libraries have some circular dependencies around startup. So, just build system improvements. We're looking at migrating the Metronome garbage collector to OMR. Metronome is the real-time garbage collector technology in J9. And what it does is it provides a guarantee about the upper bound for pause times in the collector. But in order to make that work, it places a lot of requirements on the consuming application, which, in this case would be J9. And as well, it's sort of a bit of an alien compared to the other garbage collectors in that there's not a lot of code sharing because it has to do things in different and unique ways. But we're hoping that once we can migrate Metronome to OMR, we can start to find places to clean up the code and kind of commonize some of the core technology that the collector is actually built on. And Metronome is building on technology that's already been moved to OMR, including the segregated heap code and snapshot at the beginning barriers. We're working on enabling runtime compressed references. So compressed references are a shorter encoding for references, and we do that by placing an upper bound on the maximum address of the heap. And then we can play, object alignment tricks to sort of stretch that limit a little bit further. Historically, this has always been a compile time decision, but in order to work to make this a runtime decision, we're having to check what mode we're in. Like, are we working with compressed references or are we working with full references? And these checks have to be sort of distributed throughout the entire code base. And I'm expecting that in order to make this performant, we're going to have to restructure a lot of the code in the garbage collector to try to make these decisions about whether we're running in full reference or compressed reference mode outside of hop paths, and just to keep that performance where it needs to be. We're looking at improvements to the object scanner API. So this is sort of an incremental step towards generalization, where we're not really changing the fundamental architecture of how this works, but we're trying to find ways to make it a little easier to work with and simplify the contract between the basic iterator API and the part that the language has to implement. And one thing that we're hoping to remove from this contract is the requirement that a language uses a bitmap to map the slots that contain references, and just overall make this code make a little bit more sense. And this is happening kind of concurrently with the compressed references work and support for flattened array objects in J9. And then this is kind of a big slide, but this is just listing off some of the functional improvements that we're looking to make to the standard garbage collector. The standard garbage collector sort of refers to our, our global collector, our generational scavenging collector, and concurrent collector, as well as compaction. So all these technologies get sort of grouped under this umbrella of standard GC. So we're looking at using snapshot at the beginning barriers in the concurrent GC. So right now, current collector has to sort of interleave GC work with the mutator, which is like a running application. And we need to do some amount of bookkeeping to track how the object graph is updated as the program runs. And we call that code that tracks how the object graph updates, we call those barriers. And existing barrier relies on this card mechanism. And it requires this sort of long phase at the end of a concurrent collection in order to sort of finally finish up the collection. And snapshot at the beginning barriers are a little bit more expensive. It's a little bit more of an expensive form of bookkeeping, but it may allow us to have a shorter stop the world phase at the end of a concurrent collection. We're looking at, just generic improvements to the concurrent scavenger, honestly, as well as to all the collectors. One interesting thing that we're investigating is the possibility of changing the order that we scavenge objects, so we can prioritize fields that are hot or accessed more frequently in order to co-locate objects that are used together, to co-locate them onto the heap. And this should play better with memory caches and hopefully give us a nice boost to performance. Of course, the open question here is how do we actually identify what the hot fields are? And then the last thing I want to talk about is a possibility of throttling garbage collection threads. So we always keep a pool of threads in the garbage collection, and we parallelize as much work as we can. And the historic assumption has been that we own the entire computer. So, if you have a machine that has, it's an 8-way machine, and it can run 8 threads concurrently, then the GC will create 7 slave threads plus a master. And in this new world of virtualization, the fact is that we don't always own the entire machine. So while we may be bringing up 8 threads, we may only have 50% of the computing power actually available to us. So what this is doing is causing unnecessary stalls and unnecessary synchronization in the collector and actually slowing us down. So we're looking at or we will be looking at finding ways to profile, stalls and, the cost of our different synchronization points in order to sort of bring down the number of garbage collection threads at runtime. Okay, so that's it for the things that we're working on in the immediate future. But now I'm going to talk a little bit more about things that we may be looking at in the long term. And this is more biased towards making OMR a more generic or more flexible toolkit. So we have this problem right now where we can only have a single garbage collector enabled or being built in a single build tree. And if you compare that to the compiler, there's a library of CMake utilities in order to sort of define, in order to sort of create or define new JIT libraries, and that sort of enabled the compiler to have a test compiler built alongside JIT Builder, which is built alongside Trill. So it would be interesting to investigate something like that for the garbage collector. The obvious alternative is that we rely on multiple build trees. So we continue to do one garbage collector per build, but maybe we make some scripts to make that easier to orchestrate. So a person can sort of type /build and build a Java garbage collector, or the default garbage collector, or a test garbage collector. We really need to focus on, in the GC, focus on simplifying the startup procedure, because in the garbage collector, we sort of have to interleave startup of the different components. And in order to call some guys, we need to have partially initialized objects elsewhere. So sometimes we end up, bringing up fake environments or fake objects in order to sort of satisfy the requirements of the API. And we have, circular dependencies between components. So this, component A requires component B, requires component A, and we have high-level APIs for bringing up the garbage collector, but they're sort of washing over what, like a nightmare of interleaved and complicated spaghetti code. And it shouldn't have to be like that. So there should be ways to simplify that startup procedure. We would also like to take a more configuration-based approach to startup. So it might mean building a support library that can identify startup parameters, as well as, how was that parameter set? Is it a hard limit, a lower limit? Is it undefined? Do we care? And it would be nice to be able to track configuration values back to how they were set, so that I could say, well, your minimum memory is bigger than your maximum memory usage. So why are these variables set like that? So we can track it back and say, well, this one was set in the environment, and this one was set on the command line. Here are the relevant options. And the garbage collector should be validating off parameters, but it shouldn't really be choosing. It's sort of a responsibility of the application, especially when you consider that we're actually still doing command line argument parsing in the garbage collector today. We want to open that up and make it so users can initialize these parameters however they want. So now I'm on to supporting different types of object representations. So one limitation in our collector today is that objects have to have a conforming header, which means that the header has the correct layout with the correct set of flags in the right place. And there are probably other ways to represent this metadata. And what we like to do is replace this direct accessing of the flags with new APIs in the object model, so that an application could implement, their own mechanism of bookkeeping for these object properties. One tricky part here is that it's not just objects that are actually located on the heap. We also have other entities that are sort of internal to the garbage collector, including a forwarding header in the scavenger and a whole header which tracks free space on the heap. And these flags help the garbage collector differentiate between these entities. So if we start to loosen loosen up on this and let the application choose the representation of the flags, they'll also have to teach the garbage collector how to implement the forwarding header and holes on the heap so that the garbage collector can continue to differentiate between these entities when it's doing its heap walks or whatever. We'd also like to enable new types of pointer encodings. I'm especially thinking about not number boxing or different types of compressed references. Right now, we control what the definition of a pointer is. So you have to conform to the representation that we need, which is basically a raw pointer or a compressed pointer. So we're looking at taking a lot of our common slot handling APIs and parameterizing them on some type of helper that the garbage collector can interact with, and that will enable the user to, or the application to, define how to read or write references from objects. We'd also like to support multi-part object representations. So currently, every object that's on the heap has to have a full header, which contains enough metadata to scan that object. So in Java, that means flags plus a class. But it would be interesting if we could find a way to sort of provide a lightweight object that doesn't actually contain a full object header. So that might mean like a data buffer in some kind of sparse vector implementation. And part of enabling that would be allowing users to attach metadata to the work stack so that, when we go to scan that, I don't know, sparse vector implementation, we go to scan that object, the application is free to sort of say, here's a buffer, here's its size, and this is what it contains, and then teach the garbage collector how to actually scan that without placing data in the header of the buffer. In OMR right now, we don't really have much in the way of allocation support, so languages have to roll their own libraries. We need to provide a generic way to access thread local heaps from language threads. Implementing allocation APIs can actually be quite tricky because you often have to interleave allocation with object initialization, with concurrent garbage collection work, with potentially, I don't know, zeroing pages. So we need to help to define the generic API that helps people build up this allocation API and interleave all this different work in the right way, in the right places. We don't really have any helpers for barrier-related functions. So again, barrier-related functions are, they help inform the garbage collector about how objects are updated. And we provide some really rough barrier code, but not really anything that could actually be used. So clients have to implement their own code, and that's extremely difficult to get right. J9 has a very large collection of barrier APIs. So what we would like to do is find a way to take that and generify it however we need to move it into OMR. One of the challenges would be to ensure that we don't accidentally assume pointer encodings if that's something that we need, or we also don't want to assume object layout or representation. And this last point is a bit of a stretch, but it might be possible to add some kind of tooling to help developers check that barriers are in place. Because it's very easy to update an object and forget to do that through a barrier. And these kinds of barriers are commonplace, but also really difficult to track down. So maybe some form of static or runtime analysis to help check barriers would be really cool. Right, and we don't have any ability, or we don't have any generic helpers to help people define GC roots, which are internal VM structures that help us locate what objects are actually actively in use by the runtime. So it'd be interesting if we could define some kind of feature that makes it easier to define rooted data structures, and possibly some form of roots that could be automatically registered and scanned. I had to put this one here. I don't really know what this would look like, but we really need to think about ways that we can integrate or provide some basic integration between the garbage collector and the compiler that people could pull into their own runtime. I'm imagining some basic JIT builder support for garbage collected references. And if we can define some kind of standard representation for stack maps, and I assume that would be standardized as like a standard binary format that was platform specific, then we could implement a stack map scanning library to help people implement route scanning in their garbage collectors. And if we could add some helpers for allocation that were generic enough that people could call them from their JIT builder or compiler-based JITs, that would be pretty interesting too. All right, and of course, barriers and making it possible to have IL that tracks how compiled code updated objects would be. Again, very difficult to get right for a user, but we could probably provide some kind of generic support for that. Okay, so now I'm on to the very distant future. So this is where things start to get a little bit more hand-wavy, and well, I'll let you guys see what I've been thinking about. So the reality of the OMR project is that we honestly don't know what the right abstractions are, and we don't know if we're building the right APIs. We know that there's a huge variety in virtual machine implementations, and I think at a certain point we have to face the reality that there is no one-size-fits-all solution. So we have to start thinking about who are we writing this for, and what does their virtual machine actually look like. But maybe we can go for it anyways. If we can find different ways to relax assumptions about the runtime, maybe we didn't really need a specific virtual machine that we're targeting, but that's really difficult to do. We've done it as much as possible, but we have to balance this this need of providing a sane, usable API with the different assumptions and constraints that we actually make about the virtual machine. So provide a high-level, easy-to-use API for languages that use bitmaps to track slots. That's easy, but then to provide a generic, easy-to-use API that could track any kind of object representation is extremely difficult. So one thing that we could do is start to move responsibilities back into the consumer and become more flexible by providing actually less functionality, which is a weird idea. But maybe we can make it easier for clients to develop their side of the GC contract by building an optional support library of different utilities. So we take the hardest parts that we think might be common for a lot of people, and we turn those into libraries that people can call into. So this would sort of simplify the framework element of OMR and start moving towards a library-based approach. And the nice thing about a library is that it's, by nature, it's opt-in. So if the abstraction doesn't suit you, you just don't use it. But even still, it may be impossible or too difficult for people to work with. So another thing that we can do is start to organize the garbage collector into tiers of APIs, where we have lower-level APIs that people can target if they need, absolute flexibility, but then higher-level APIs if it suits them. So this might mean something like extensible classes or some form of providing a default implementation that could be overridden by the user. So what this might look like is where we have our core garbage collector technology, which is calling into these low-level delegates, and these provide the low-level needs of the garbage collector. So these are all the most basic questions, and there's no attempt at factoring code into clean, reusable interfaces. It's just I need to scan this object, but I don't know how, so language, go scan the object. And what we can do is build these optional adapter libraries, and it could be, a CMake library that injects sources into the client that implement those delegates in terms of higher level interfaces. So if you're like Java and the slot iterator API works really well for you, then you enable the adapter, implement the iterator, and then all the delegates just sort of get implemented for free. I think that, maybe this looks good on paper, maybe it doesn't, but I think really in practice, we don't know how well this will work. In order to build the kinds of abstractions necessary to actually implement something like this, we might end up, coming up against the limitations of C++, the language. Even if you could write code like this, could you actually understand it? And then, would it help anybody? So, do we know that the places that we've chosen to as our layers of APIs, are those the right places, and are these the right APIs at each level? And if nobody uses it, what was the point of writing all this in the first place? So maybe we can help or try to reduce the risk of this kind of work by taking an incremental on-demand approach, where when we find that one particular API works well for one or for a few people, but doesn't work well for others, then we start to break it down into layers to figure out where do we have to split the APIs on in order to support as many people as possible. But only take that approach if we actually need to. And maybe this is I don't really see this as, it's not a competing practice compared to extensible classes. I kind of see them as working together. And they could sort of be implemented in terms of each other, but maybe this is a stepping stone towards unifying how we address extensibility in OMR. And that's it. That's everything. So,
thanks, Rob. Any questions for Rob?
I have a question.
Yeah.
So one of the challenges you were mentioning is it's unclear, like even what, like who is the target user for the garbage collection technology?
Mm-hmm.
Have you thought about how you might go about answering that before trying to jump into a very flexible design unnecessarily?
Right. I think that this was just sort of an idea about where things might go in the future. I'm actually not advocating that we do this, especially not right now. That's part of why I was saying that we need to take an on-demand approach. So we wouldn't actually start to do this until there was a real need. And yeah, debatably, there is no real need to start doing this kind of work today. But if we ever found somebody, that's where we start to apply this idea. Anything else?
So of the near-term things that you had earlier on in the talk, do you have a kind of feeling for how far out that gets you? Like, is that a month of work? Is it 3 months of work? Is it 6 months of work? Is it this year?
So that would be sort of like the near future items, which would be like the builds and metronome. I think it really depends on which particular work item you're looking at. Certain things like retiring the autocomp builds, I think that we could accomplish that pretty soon. But other pieces like actually migrating metronome to OMR, who knows? It could be. Some of these are quite big jobs, so I think we're looking at least to the end of the year. Yeah. Well, for some things. Yeah.
So one question that I have is that there's been a lot of work done with demonstrating, building interpreters and that kind of thing with OMR. There's been quite a lot of stuff done with JIT Builder and other things to demonstrate how to integrate the JIT with another language and trying to make it easier for people to onboard. What are the plans around the consumability aspect of it and trying to make it easier for people who want to try out the GC and make it easier, or even provide some level of initial integration with an interpreter or JIT?
Well, I think that the most significant challenge for people when you're looking especially to implement just a basic global collector would be the object iterator interface, or the object scanner interface, and we are looking at improving that, and I think soon we're going to have a better story for that. There are other challenges that we're aware of, especially I think with barriers and working with the concurrent collector and defining your own allocators that can sort of orchestrate the process of allocating an object correctly. So I think a lot of the things that we're looking at in what I call the distant future sort of help to make OMR easier to work with. And it's not all just about making OMR more generic, but also providing more functionality so people have less to do.
Do you have any particular integrations or things in mind that will serve to help prove out the ideas? I mean, things like the WASM JIT, LLJB, things like that have certainly had an impact on how JIT Builder works and how the people who work on the compiler component think about our interactions with other languages outside of OpenJ9. Do you have anything like that that will help prove out the ideas or the things that you're planning on doing?
The things that come to mind would be the default object model and base 9. Well, although base 9 is moving to be based off of the default object model, as well as the example code. Those 2 or 3 things, and and so on. So yeah, there are things there are alternative runtimes that we're looking at and have looked at in the past.
Okay, thanks.
Yeah.
Okay, any more questions for Robert? No? Okay. All right. Well, thanks, Rob, for the overview. Looking forward to seeing some of these implemented in the various stages of the future. Okay, that was our last topic for today. So if there's nothing else, we will adjourn for today.
Cool. Thank you.
Thanks, everyone.
Bye.